Welcome to lecture number 12 of module 2. In lecture number 11 we saw that the voltage stability for the radial system, and that we can analyze if a system is radial by the PV curve. Again, to recap that, here I use this system, that is a system which is feeding power. It may be your generator, it may be a substation, and that's a line that is a connected radial line is having Jx, let's suppose R is very less, and it is feeding a load of P plus jQ. For this, as again I can write this power flow which is flowing here, this P value, and the Q value we can write these two equations. If we are eliminating here delta from these two equations, we can get equation in terms of V, and that will be order 4, and other terms will be getting. So means it will have the 4 roots. 2 roots are impossible because they will be having the imaginary term, and imaginary voltage is not possible. So the remaining 2 we can get the V1 and V2 by this equation, and you can get it very easily. So for the different P and Q, we can plot the curves, and we plot the curve here that is called the PV curve. Means if your x axis is P and your y axis is your voltage magnitude at the load bus, then we can get this here curve that is called PV curve. This point at this tip here, it is called the notch curve of this. If you are again now for the different power factors, here the curve will be different. If this is for your unity power factor UPF, this curve which is here, that is coming, you can say this curve. Then if your power factor of that load, that is a Q, you know the Q, if it is a plus or minus. If it is a minus, means that is your leading power factor load, and for that you can see our curve is here. Now what we can see here means this P at this node, this is the called the P critical, and it is the voltage where we are getting, that is a voltage critical. Now if your power factor is leading, you can see you can go critical loading, means maximum load that you can get here, that is a more than this. So this shows that if you can improve the power factor of your load, you can load your power system without losing the instability due to the voltage. Because here now you can say if your power factor increased, now we have increased this much margin, and then you can consume more power. Similarly, the reverse is also true, means if you are going for lagging power factor, means it is your P plus jQ, here Q is positive and P is positive, then it is for the leading, again this curve is keep on reducing, and you can see you can only this load up to this critical value here for this power factor, and again if your power factor is worsened, you can load up to this critical values. So it is not possible to go far beyond that, because it is not your system will be unstable, and this is basically this is true for your radial power system. You can also see the QV curve. This is your Q and this is your voltage curve. This is basically very well known, the QV curve. In this QV curve, you can see the curve here is approximately is just like a V curve. Means it is, you can say this V and further different. So if you are keep on increasing your power, if P is more, you can say the Q requirement is going to be more and more, means you can say more Q is going to require for the same voltage. If suppose your voltage here is a fixed value, so then we can see the power increase, the Q increase will be more. So in an interconnected system, it is easier to draw QV curves than this is a VQ curve than your QV curves, but at which this VQ curve is being obtained is treated as the PV type bus, which specified voltage value is where the voltage V. The load flow results give the corresponding Q value, means you can keep on increasing your load, that P, and then you can solve your power flow equation. So then you can get the voltage for different P and Q. So if for that, for any bus you can get the V and Q for various load increase, you can draw a curve and you can find this Q. So this also gives the information about your system stability, and this here, these are the nose points. Now let us see the effect of the load type and the generator Q limits. Here let us suppose your normal case, here just I have represented as the first curve, that curve which comes through here, this is your curve, this is your P and it is your V. So you can say for any given load, let us suppose your constant power load here, this curve is a constant power load, you can see we are getting two intersections for here. It shows that we can have the two voltage solution, one is very close to your operating point and other is unstable zone. So this voltage is basically actual operating, where the voltage of the system will be this one. Now you can see if your system is stressed, means again the highly stressed system, you can have another curve here that is 2 like this, means you cannot load more in the stressed system. So you can see this line is not intersecting this, it means that it is not possible to go for this much amount of power, because the maximum power here will be only your critical power, that is a P critical here. You cannot get more power on that bus. Now again you can assume that if there is your load is a different type, here the voltage sensitive load we have, and it is a just if P is changing, your voltage is also changing, and this is just like a quadratic curve, you can say, means your P is proportional to, let's suppose, V square. So here you can say now the intersection here, it is this and it is this. So for the normal case you can go up to this loading, and this will be operating point for the normal, and for the stress you are going for this one, and this will be actual operating voltage. Now let us take the violation of Q limit. You can see what happens, your system is just following this at any certain point, means if you keep on increasing the power, this is your power increase that is here. Once you are taking more power, there will be possibility that the Q limit of the generator is violating, means it is here your generator, this is your feeding a line, and this is your load. So if you keep on increasing, this generator or substation will have some limited reactive power generation. So if it is hitting this limit, what will happen? Suddenly this value will be dropping here and voltage here, and then it will have another QB curve here. Now in this case, if it is violating, now you can see our critical loading, that power that we can load here, we can get the P, now again is much less compared to your stress system as well as you can say normal system. So this is your curve 3. So the impact of this Q limit, if you are having more reactive power, infinite let's suppose reactive power, then you can have this normal curve, and then you can load as much as possible up to this point. This is the critical loading. So we can see if the violation of reactive power limits of the generators are reaching, then our PV curve is reduced, and then also we can load less reactive power. Now we can again see the impact of the online load type changing transformers. Already I explained what is OLTC in the previous lectures. So this is again I have taken a system that is here your system, that is a substation or you can say generator, that is feeding a resistive load, let us take, that is R. Here the voltage is V prime, here bar means complex voltage, here we are taking angle 0, means here we are getting angle 0. Reference is your this, and the voltage here it is changing, means this is your angle delta. So the power will be flowing from this end, and this load is consuming power. Here we have a line, this is your transformer, and this transformer having the turn ratio that is 1:n, means here you can see your V1 over V will be your 1/n, means this voltage divided by this is N1 upon N2, so we are getting this ratio. So now we can see your this V will be NV1. Now whole all the quantity, we can represent completely the complete system here. Now we can, if we are ignoring ideal transformer this side, so we can write here, this is your line reactance and this is your V, this is your R, this is voltage V, and this voltage will be transformed, and this your J, here X N square, and here this we are getting this here, it is upon N square. So this voltage, or you can say the V1, I can write V1 will be your V upon N. So this voltage we are just putting this side, so we can have this voltage sort of this, sorry, it is not N square. Now again this is R, and then route we can write the power flow equation, that is a P, and we can write again the voltage equation. So if you are writing the voltage equation in terms of P and Q, and then this voltage again you will be getting your V1 and V2 as in the previous case. Here only this X is changed, you will get V1 and V2, and from these V1 and V2, if you are going to differentiate this, that equation, you are going to get this much. This is your expression, and this is called the sensitivity, means your change in the voltage with the change in tapping. Means if your tapping is changed from V1 to V2, how much voltage is changed, and this shows that whether this value is positive or negative. From this expression we can say at the normal loading, this R is greater than N square X. So here this sensitivity factor will be the positive, and this is called the normal action of your OLTC, means this value is positive. At the higher loading, what happens, this R is less than N, because higher loading means R is very less compared to this X. So this we can say here this may become the negative, and this shows that it is a reverse action of OLTC, means it shows that if you want to change the tap, your voltage is decreasing. If you are increasing the tap, here from here you can see what is the positive and negative. It shows here it is your voltage, you are changing the tap, voltage here V is increasing. If you are in this case, in highly loaded case, this is a reverse action, means if you want to increase the voltage by changing tap, as usual once you are going to change the taps, if you have more taps, more voltage in the normal conventional way in normal loading. But this reverses, because here you can see the sensitivity becomes negative, means if you are increasing the tap, voltage is further reduced, and this further reduction in the voltage will cause further collapse and keep on, means it your voltage here like this is your keep on reducing, and finally it is a collapse. So this is a reverse action of OLTC that is very severe, and that is especially in high loading condition. When from this equation you can say this R plus N square X here, this is always positive, here R minus N square X, that is only coming here. So this value can be negative or positive, because the here denominator is always positive. So this depends upon this factor only, and from here whether we can get negative, that is positive, or negative we can decide, and it depends upon whether R is less than N square X or it is more than that. So this you can say the reverse action shows that when you want to increase the tapping, in for example if you are increasing tap for increasing voltage, but the action is reverse, means your voltage is decreasing, and further your transformer will try again further and further, and finally voltage will be collapsed. So this is also very adverse phenomena in the voltage stability case, and it only happens at the higher loading. Again, sudden change, for example if you want to change, in OLTC as I said, it is online load type changing transformers. They are the under loading, it is there will be some sensor circuit, it will try to change the tapping to maintain the voltage. And here you know for the increasing voltage of the V, to want to increase here, no doubt N must be increased. But in the reverse action of OLTC, if you are increasing this, this is decreasing, and that we don't want, and but your the sensor everything it will try to increase, only the typing option is there. So here it is one case of the voltage collapse. In other, just I want to explain you the effect of sudden change in the transformer OLTC. Suddenly it is changed. What is happening? Now let's suppose you are operating at N1, that is some fixed tapping. Your PV curve follows this. Again here I have drawn the PV curve. Now at certain point, what you are doing, you are just maintaining this N1 constant. If reduction of the voltage goes beyond certain value here, suddenly we are increasing the tapping, means we want to increase here. What happens here, the voltage will be trying to constant and it will come here, and you can see at this N2 tap our PV curve will be this was. What it shows that now after changing from here to here, this point A was stable, but here it is going to point B, it is unstable in the sense of voltage stability. Okay, why? It is less than the nose point and is below this. So this portion from here to here, it is unstable zone, and this only this upper portion here, it is your stable case. So you can say suddenly change is also very dangerous, and it may lead to your unstable zone, and here once it has landed here, now it is keep on reducing and finally your voltage will be going 0 and your system will be collapsed. So this is also one concept. Means OLTC transformers sometimes also they try to, although they try to improve the voltage, but sometimes they also give the voltage instability case. Now let us see the what are the, and all these cases basically why the OLTC this is happening. This voltage stability problem is related with the reactive power of the system, because the tapping changing, you know that tapping here is nothing, a transformer, let us suppose here is there, and if you are having some taps here, what happens, this transformer can be represented by here and a pi equivalent here, the shunt parameters here. If here it is A is to 1, I can write here the admittance of this is y I j, it is upon A, and here it is y I j 1 upon A minus 1. Here it will be a 1 will be capacitor, 1 will be a inductor. So this is nothing but it's effectively just we are representing as a pi equivalent. What it does shows that one side it is providing just like a capacitor, one side is absorbing. So again we are going to try to mismatch the reactive power, means somewhere injection, but no doubt this total will be 0. So this voltage here is increased, this voltage is decreased, and this is the action of that. So basically all these voltage instability phenomena, this is the case of the reactive power, and that is the reactive power requirement in the system. What is the reactive power status? That is reactive power loss as well as the reactive power generation. Now reactive power is consumed not only by the most of the networks element like lines, transformers, reactors, they absorb the reactive power, consume reactive power, but also it is consumed by the loads. You know the most of the loads they are lagging, they are operating lagging power factor. Why it is so? Because what are the loads right now? Most of the loads, it may be your induction machine, that is nothing but your induction motors. So they operate, you know, it is a lagging power factor because they consume reactive power. We are having some bulbs here, and these bulbs basically pure resistive, so there is a unity power factor almost. We have the tube lights, and these tube lights work again on the lagging power factor. So the most of the loads except synchronous motors, our here the power factor comes in the lagging nature. So the most of the loads operate at lagging power factor and are very sensitive to the load. So if reactive power cannot be transmitted, it ought to be generated wherever is needed. And also this reactive power or the voltage problem is the local phenomena. It is not possible to transmit the reactive power from very far end to the load center. However, the real power, it is true. For example, you can see in a practical power system, a generator will be generating power very far from the load center. You can take the example of the UP Power Corporation, where most of the generating stations are thermal, they are lying in the Sonbhadra district, that is Obra, your Anpara, and also we are having some central that is the NTPC power generators. Those are Singrauli and Rihan, and they are great hub, and they are generating more than 4000 megawatt power there. And then we are transporting those power to our load center like Kanpur, Lucknow and Delhi side, or Noida side and Ghaziabad, etc. So what is happening there? We are transporting the real power. At the same time, reactive power, it is not possible to transmit from those generators to again from Noida and the Ghaziabad and Delhi side. So it is, if it is not possible to transmit, again the possible due to the line constraints and other things, then it must be generated locally. So we have to compensate those reactive power by generating locally in the local load centers. So reactive power sources mainly are no doubt the synchronous machine, those are generating the reactive power. First, of course, the alternators are generators, and another is your synchronous condenser. Synchronous condenser is the case, it is nothing but an alternator. It is an alternator which is generating the reactive power, but the P generation is 0, means there is no electrical power generation, it is simply running and it is improving the reactive power, then it is called synchronous generator. Normally it is not true, but what we do, we can have a synchronous motor where the mechanical load is 0. Now basically condensers are here, they are the motor, nothing but they are the motors where there is no load on that motor, but it is rotating and we are just providing the reactive power to the system to improve the system profile, a voltage profile of the system. Another reactive power source is your capacitor, and again the capacitor putting in a high voltage network is very difficult, means EHV as well as UHV transmission system. So we try to put these reactive powers through the capacitors in the distribution network. So the capacitors are normally installed near to the load centers so that it can be compensated, the requirement of reactive power of the loads are met locally, so that we should not flow the reactive power over the transmission line. Another source of reactive power is no doubt the line, but that line, once it is lightly loaded, it can generate the reactive power. Means here, if again we can say this is a line, let's suppose it is having X. Here this will be your the loss here in the line that will be consumed reactive power is I square X, if it is a X here. At the same time, as we know that we are having the distributed parameters, that is the charging capacitance of this line, and that can be represented by here the pi equivalent, that is a capacitor. So these are injecting the reactive power, and that is nothing but V square upon your Xc. So the total reactive power which will be supplied by this line is nothing but, whether it is supplying or absorbing, it depends upon your I square X minus V square upon Xc. So if this value is positive, means this line is absorbing the reactive power. If this value is negative, means this is less than this, so we can say it is generating. And when it is that, if I is less, means loading is less, then this component may be less than this, because V is normally the rated voltage, the variation is very less, but this I can be from 0 to its critical loading. So then this line can generate, and especially this is the case when the system is lightly loaded, and for example in the sometimes monsoon seasons or somewhere in the off-peak hours, even though in the midnight onwards the loading of the system is reduced. So this value, this line can generate reactive power. So the factor affecting the real power is mainly the voltage phase angle difference, this voltage phase angle difference and the transfer reactance, because we know this P is nothing but, if you remember, it is your sending end, it is your receiving end over X sin delta. So this voltage we know it is very less affected, because voltage change is not so much, but if X is changed and the delta is changed, so P is very much governed with the X and the delta. So the mainly the voltage phase angle difference, that is a delta, and the transfer reactance X are the major factors, those are affecting the real power flow in the transmission lines. Consider a radial line having reactance X and sending end voltage is Vs angle delta and the receiving end voltage as Vr angle 0, means we are taking as a reference. if the sending end power is PS JQS and the receiving end power is PRQR, then we can write this PS here will be your nothing but that will be equal, the sending end power will be equal to receiving end, again I am talking about the real power, will be equal to your sending end voltage magnitude multiplied by your receiving end voltage magnitude divided by X sin delta. However, this reactive power, this Q that is from the sending end, basically what we did here, it is your Vs angle delta, and we have the transfer reactance of this whole system. Here it is your receiving end, this is your Vr angle 0, and here I am taking it as a Jx. So this is your P plus JQ. Yes, this is sending end, and here receiving end we are getting what we are getting. We are getting here, that is your PR plus JQR. So this PS and PR will be equal because there is no loss. Here I have assumed this line is lossless, and then we can write this your PS will be equal to your PR, and it will be equal to your Vs magnitude, although here we have taken magnitude, here Vr magnitude divided by X sin delta. So both will be equal. Now, but the reactive power supplied source SQS will be nothing but here you can see it is, I can again slightly, it is not clear, here X, and here is a Vs minus Vr cos delta. Now again we can see that this Q is positive or negative, that depends on this value. Since this value is very close to unity, so it depends upon how much your Vr and Vs and Vr. So if Vr is more, means here it will be supplying the reactive power. So this variation if we can ignore very less, so we can say if your Vs is more than Vr, then it will be positive. What it does mean? It shows that the reactive power flows from higher voltage to lower voltage. Especially it is true only in case of the EHV transmission line when this is very small. So it shows that this will be flowing here. Now however the QR will be the here the different. Here it is a QS delta cos delta minus Vr, and here Vr upon X. This side this depends upon this voltage. So this profile of this here the reactive power generation, I can see the voltage here. Let's suppose we are maintaining the voltage somewhere at 1 per unit. So voltage may be here again like this, or it may be this. If this Vs and this is your Vr, so again it depends upon the loading of the system. Here this is called flat loading, here it is called lightly loaded because the voltage is more in the line, and here it is heavily loaded and it is a sagging case is there. So just I have taken one example for the same transmission radial system where this line is having the reactance, that is X is equal to 0.02 per unit on 100 MVA base. The value is keeping the sending end voltage just is kept for one case 1.0, and the receiving end voltage is 1 per unit. Angle for the given load it is 5 degree. We calculated this QS and the QR, and we found that QS is here 0.28 and your QR is 2.38. It shows that your system is lightly loaded, and your here the Vs is more than your Vr, and your this reactive power here the transmission line bus here that is flowing from here is more reactive power, and here it is going less reactive power. It shows that line is consuming some reactive power inside that. Again further we reduce the voltages again by 2 per unit here, 2 per unit here, and then what we did, we just saw for the delta again for more loading, and again for more loading the voltage will be less. So we saw the reactive power requirement will be very high here, and this is here going out, that is very less. Now in this case the loading is more than this degree, you can say the loading 5 degree to 15 degree, means it is almost you can say very high value, that is increased. So it requires more reactive power from the source, and here the reactive power which is flowing is very less, that is almost 0. Now you can further reduce the voltage, and if you are here, this angle is changed more. We can say the reactive power generation here is almost here 88 MVAR. However, the other side, that here it is negative, it shows that reactive power is again consumed by this line, and the reactive power is flowing inside this line. So here this is again, if you will see the profile of this line, the voltage profile, this is your, I can say one axis here, this is 0, here let us suppose 1 per unit, here it is your VR, it is your 98, one case 98, so here 95, let us suppose it is 95. So what is happening, the voltage profile, it is a reactive power flowing from higher to lower voltage. Here also, so your line profile will be like this, because we are maintaining the voltage, because the reactive power which is flowing from here to here and again from here to here. In another case here, what happens, it was 1.3 and here 0.98, the reactive power flow are like this, means reactive power is flowing here and here is less value. And another case also, it was for 1, it was like this. So if your loading is increasing, this line is unable to transmit, you can say what I want to say, here the reactive power was transmitted, here the reactive power was almost not transmitted, just you can say this only completely this line is absorbing. In this case, it is taking reactive power from both ends. So at higher loading, it shows, whole this analysis suggests that the transmission line are unable or find difficult to transmit reactive power at this higher loading. The reactive power also depends on the angle difference during the stress condition, no doubt this angle is also very important, and the PV and Q delta decoupling does not hold good. Normally, you know that in load flow, what we take, this PV and the Q delta decoupling we take, means we assume this P is coupled with the delta and Q is coupled with V, and based on that we normally go for decoupled load flow or fast decoupled load flow analysis. We are taking the solution. But in stress cases, it is not possible, that we cannot take these decoupling, and then we have to go for the intact system and without considering the decoupling as well. To see an example of simultaneous voltage and angle stability, here you can see this is area A. This grid with the good voltage control in area A and area C, they are having very more reactive power and they are very strong in terms of voltage control. The voltage for the normal operation and the weakened grip, here if the grid is there, there is another system that is B here, and they are connected with the tie lines. This system is very small, this system is very large, means they are having enough reactive power support Q, and here also they are having enough QC, here QB. So power is transmitting from A to C via B. If one of the line here trips open, what happens? During the grid intact, you can see the voltage here is very fine, here almost equal VA, VC and V3, voltage here, here and here is almost same magnitude, and then you can say we have less angle. If this line is tripped, what happens? Now you can say the voltage of B is reduced, angle is increased, so both angle and the voltage stability coming together in this case, because here this impedance is reduced and this X is here more, and we can transmit more power, means delta is separated more. So here you can say the delta is more, and also the voltage at the B is reduced. So here is a combination of voltage as well as angle instability. Normally for whole analysis, we analyze this reactive power up here, means that is a load flow Jacobian, this is called Newton-Raphson power flow equations that we solve in polar coordinate. Here again just I want to give brief about load flow. Now question again arises, why we are using del V by V? Why not V? You know, the mismatch vectors for power, it is change in real power and change in reactive power. We go for the here Jacobian matrix. Here we go for the change in the state vector, that is a delta, and change in V. But here in the Newton-Raphson load flow, we normally divided by V. Here the question arises why. The main reason for this, if we will go for the differentiation for this J1 and J, here J1 and J3, because you can write this P equation here, it is here J1 is nothing but the element, it is your del P upon del delta. Here you can see this P is a double summation here Vi Vj, again it is a function of cosine and delta. So this is a quadratic of voltage. If you are differentiating with the differentiating this equation with respect to delta, we are getting still the quadratic here of the voltage. But here if you are going for the J2, it is nothing but your change in P by V, means one V goes off. So we try to multiply this to make it quadratic. As you know, the Newton-Raphson load flow method is provides basically your quadratic convergence. So we basically multiply here with V and here we go for V. So what has happened? This multiplication gives complete quadratic and then we get the faster convergence. So this is your Jacobian. If you are not changing the real power injection here, so what happens? This will be 0, and we want to see the relation between your change in reactive power with the change in voltage. From these two equations, now I can write, you can expand the first one. So it is a J1 delta plus J2 del V upon V here is equal to 0. From here what we can write, this change in delta is nothing but minus J inverse, J1 inverse, here J2 change in V upon V. If you write this second equation here, we are getting change in reactive power, it is J3 change in delta plus J4 change in delta V by V. If you are substituting this delta here, we are going to get change in reactive power Q will be here, just you have to put this and with the negative sign. So I can write here J4 minus J3 J1 inverse, here J2, and here in total change in voltage by V. So this called your JR, that is called reduced Jacobian, and this gives information that the change in the reactive power with the change in the voltage at the any bus we can get that factor. So this is the reduced Jacobian, and this gives a lot of information about the system voltage instability. So normally for the voltage stability analysis we use this Jacobian rather than only either J. Here we don't use this one, because if you are going for coupling, normally this equation we ignore it and we can say this is 0, and we can simply say delta Q is your J4 change in V upon V. If your lightly loaded system is there, so this equation is valid. But for in all cases, whether it is lightly loaded or heavily loaded, we can go for, instead of J4 here, we can replace here, it is a JR, and that is called reduced Jacobian. So this gives very good information for analysis of the voltage stability. The major methods for analysis of voltages, basically here I am talking about the voltage instability or stability analysis. Our first one is the repeated power flow, that is your repeated load flow. Power flow is similar to load flow methods, along with the singular value decomposition, or another method is your eigenvalue analysis. Another method here, the main problem here in the repeated power flow method is that this repeated power flow methods may not converge when your system is highly stressed, and especially at the nose point. Just we saw the PV curve at the nose point, this Jacobian becomes singular, means your this Jacobian here, this will become singular and you cannot get the inverse, and if you cannot inverse, then you cannot solve. So what happens, this repeated power flow sometimes very difficult to get that value at the nose point. So another method, that is a continuation power flow methods are there, and that uses your predictor and corrector steps, and the two methods are coming together. Here we use the predictor and corrector. Advantage of this method is over this repeated power flow method. Here in the repeated power flow method, if you are using very good method for the load flow analysis, here as you know this is a PV curve, only you can get the solution up to the upper portion here, this portion. This unstable curve you cannot get. But here in the continuation power flow, so just I was explaining the advantage of continuation power flow over the repeated power flow method. Here in the continuation power flow, again I will explain how that we can get the power flow solution using this continuation power flow method, and that is I will discuss the steps, that is the predictor as well as the corrector method. But here I would like to explain that in this PV curve, here this is your PV curve, we can get even though lower portion of this curve as well. So we can get no doubt this and as well as here, and we can go up to the nose point without any problem. In this method what we do, first we go for the start from some initial guess, then we go for the predicting this, then we go for correction, then we prediction, correction, prediction, correction, prediction, correction, and finally we converge here, and similarly we can go for the lower step. So here it is a corrector step, this vertical axis, and here horizontal is your predictor steps, and thus we can achieve this complete curve, that is the upper as well as the lower size, and this is very popular method for the voltage stability analysis. Another method, that is third method, is called your direct solution method. That in this method means we can determine the voltage stability boundary using the eigenvector approach. Means here a system that is in number of n plane, we can get the boundary, and in that boundary that we can use the eigenvector approach, and then we can say whether your existing point is well within boundary or it is outside or it is on the boundary, and then we can assess the system voltage stability. Another is your optimization techniques, that we can measure that how far we are, and using that method we can determine our the voltage instability case. Now let us see, the first one is your singular value decomposition technique, that is very popular and very, you can say, that can be used. Here this the Jacobian matrix, complete Jacobian matrix, if you are having n bus system, then you can form the Jacobian matrix this n, and which this is the order n cross n, that can be decomposed into this form, that is the Jacobian matrix. Here we are having the two vectors, orthogonal vectors u and v, we can form in such a way that this matrix D becomes a diagonal matrix. So this D is nothing but your this having these elements, only diagonal elements, and these diagonal elements are known as the singular values of this Jacobian J, and they are represented as sigma 1, sigma 2 to here sigma n will have n value, and they are known as the singular values of them. These values are nothing but, we can also, instead of going all this, we can determine the sigma 1 and sigma 2 by getting another matrix here, this J. This J transpose J, you can say it is a square of the J. So if you are getting here the eigenvalue here for this complete matrix, not J. So if you are getting that here lambdas, so the square root of these eigenvalue I, it is nothing but your sigma I. So you can, what you can do, if you are having the J matrix completely, you can multiply with its transpose, pre-multiply, and then you can determine the eigenvalues. So you will get the some eigenvalues, let's suppose lambda I. This lambda I is not an eigenvalue of J, it is a eigenvalue of the combined J transpose J matrix here. And then after that, if you are taking the square root, you will get here the singular value, that is called sigma I. When this J approaches near to the singularity, means if it is approaching for the radial system, let's suppose here, the Jacobian become singular. So once it is approaching near to this singularity here, this point is singular point where the Jacobian this J, the determinant will become 0, means it is a rank deficit we also call. So, the minimum singular value here, this sigma n, what will happen? The eigenvalue of this one eigenvalue will have 0, and means this j min will have 0 value. So, this will also approaching the 0 once this j is approaching to singularity. So, this singular value gives information that where you are, how much that your system is operating, how much away from your voltage instability, means how much away from this notch point. We use normally another number that is called condition number, and that is defined as here sigma max divided by your sigma mean. This assumes large value and approaches here, means from here we are getting sigma minimum also, means we are having sigma 1 to sigma n, means we are having n values. Out of that, 1 will be minimum, 1 will be maximum. So, from that we can, what we can do, the sigma max upon sigma min gives your condition number, and this normally is very high or even though infinity at the when j approaches near to the singularity here at this notch point, because this becomes 0, means this becomes infinite. Now, you can see the curve for this variation. Once your loading is keep on increasing here, if loading factor is increasing, this your condition number you can say here it is a keep on increasing, whereas your this singular value you can say keep on decreasing, and finally here it is becoming 0. So, this shows that your condition number is increasing, or you can say your singular value is minimum is decreasing. So, either you can use the condition number or you can use this, and then you can see how far this is your critical loading, where you are, what is your this value of lambda min, then you can say you are at this margin. Similarly, from here condition number you can say how much you are away from your critical loading. So, this gives your margin, and that is again it is the static voltage stability margin. Here this is notch point, and then how away you are operating your system. So, this approach is known as singular value decomposition approach. Another approach that is again I was explaining that the eigenvalue analysis approach, and that is again comes under the repeated power flow method. In this what we do, the system dynamics can be considered by augmenting the power flow equation to include the dynamics. That is, the system dynamics include your generator dynamics, your exciter dynamics, your load dynamics, your other whatever the parameters you want to include, and then those device you can say dynamics equations you can include. So, the many models are possible, again with how many these equations you are using, and that can be included there. So, we can write the common type of a system model, that is a mix of differential as well as the algebraic equations. That is here the system dynamic model of generators, exciters and other load parameters, models. This is your nothing but your power flow equations, and that is your equality constants. So, this is combination of you can say mixture of differential. Here is a differential equation. This x dot again is nothing but your x dx upon dt, and x is the state of the power system. So, here there is a 2 x and y are variable, and what we can do here again this now called the DAE here, because the differential algebraic equation we call it. This DAE equations can be analyzed by linearizing around an equilibrium point and calculating a reduced Jacobian. Means again we can linearize this equation, like here you can say we can differentiate this here, that is your change in x dot will be here I can say your change in f x, and here change in x plus your f here dy, and again here change in y. Similarly, we can write for here, and we can write a Jacobian matrix here J. Expanding this equation and eliminating this your change in y, here this is 0, if you can eliminate here from this equation. So, we can get a equation in terms of this, or linearized relation in terms of reduced Jacobian is obtained. So, and we can obtain like this. What happens from here, we can write from this equation you can see, means again let us here we can write in terms of Jacobian terms, let us suppose J1 and J2 it is better, J1, J2 here again, here J3 and J4, and this is your change in x change in y, here corresponding to your change in x dot, and here it is your 0. What we are going to do from here, from the lower equation, we can write again, this is your change in your x, it is your j3, plus your j4, change in y, it is your 0. However, your this change in the differential equation here x, it is nothing but your j1 change in x plus your j2 change in y. From here we want to replace, means I can write change in y. Actually x and y are the vectors, the various states are there, various here y states are there. So they are vectors, so it is not one quantity. So I can write here it is equal to minus j4 inverse. I can take this side and then I am just dividing here, it is j3 change in x, and this value if we are trying to replace here in terms of y, so I can get this x dot will be your j1 minus here j2 j4 inverse j3, and here we are getting change in x. Now this matrix is called the reduced JR, and it is the variable of x only. Now this matrix will give the information about your, again now it is just like a steady state your power flow Jacobian, and here we can analyze this matrix and then we can get the information about the condition number and other thing, and we can say the system stability conditions. So here we can analyze using the eigenvalue, we can go for the eigenvalue of this matrix, and then based on that we can conclude several information. So that is if all the eigenvalue of that system Jacobian, which I said here it is a JRX, it is not a power flow Jacobian, it is a different than that, because the power flow Jacobians are included there itself. Means here in that case we have used the dynamics of the system along with this one. So if eigenvalue of the Jacobian, means all eigenvalues are having the negative real part, then system is stable, no doubt about that. At maximum loadability, or you can say the static voltage limit or saddle node bifurcation, one of the eigenvalue becomes 0 and other have the negative real part. What does it mean? It shows that here in this case, if you are reaching here, as I said, the Jacobian becomes singular, means one of the eigenvalue here, that is a lambda I for this, will be 0. So this will be 0 and other will be, only one will be 0 and the remaining will have the negative part. So at the higher loading condition here, this and that condition is basically saddle node bifurcation case, means nose point, or you can say static voltage limit case. So we can obtain by knowing the eigenvalues. We can also determine the participation factors, and that is called, if you are using the participation factors, then it is called the participation factor analysis. In that we can have the different participation factors. It can be your bus participation factors, it can be your branch participation factor, or it can be your generator participation factor. The bus participation factor is the same as the state participation factor which we defined when I was talking about the small signal stability. It is nothing but it is the multiplication of your the vectors which are obtained, that is a right eigenvectors and it is left eigenvectors, and then we can get the participation factor. But it is corresponding to a load bus state. It is not a normal, it is if we are taking the bus state of the bus, load bus, then voltage participation factor can be this. The element of participation factor corresponding to the critical eigenvalue, you know, just for each eigenvalue we will have left eigen and right eigenvectors, and then we can have the participation factor. So for the critical eigenvalue that we can go, and critical eigenvalue is when we are getting the minimum critical value, that is here in this j axis, how close this to the 0 point. The branch participation factors, when modal reactive power corresponding to only critical mode I is perturbed by unity. These factors are defined as PJI is the change in reactive power loss for the branch I divided by the maximum reactive power loss for all the branches. Similarly, the generator participation factor, when the modal reactive power corresponding to only critical mode I is perturbed by unity. These factors are defined as PMI, that will be equal to change in the reactive power generation of mth generator divided by the maximum reactive power change for all the generators. These factors are used for the placement of shunt compensators, series compensators and the generator controller to improve the static voltage stability. So, knowing the eigenvalue, we can go for these participation factors and then we can use these factors for improving the voltage stability. Again, here till now I am talking about the static voltage stability, and that will be used for that. Another is there is a very important, that is your continuation power flow method. This continuation power flow method, as I said, that can be used to get the upper and the lower bus voltage limits as well. So far we have seen that the two methods, that is again the methods as I explained, there are the three methods for analyzing the static voltage stability, that is your repeated power flow method, that includes the singular value decomposition techniques and your eigenvalue analysis, and we saw that. Another that is very popular method is continuation power flow methods, and most of people are using that. In continuation power flow, there is an advantage over this repeated power flow, that at the notch point, at the saddle node bifurcation point, that it is not possible to get the solution because Jacobian becomes singular. So, we can approach very close to that if you are using very powerful load flow solution, but we cannot get solution at the notch point, and also we cannot get the solution for the lower voltage. It is sometimes we can get, but it is not always true, because your initial guess must be different and there may be always chances that you will get the converse solution. Another, as I said, the optimization, another I will discuss about this boundary criteria, that we can measure that how far we are from that boundary, and then we can say your system is stable. So, for in this whole lecture, this lecture number 12, I explained that the effect of OLTC, that is once OLTC is operating, normally the all-line load tapping transformer tap changers are used to improve the voltage. It is sensing the voltage, and whenever the voltage is less, it is trying to increase the voltage by changing the tappings. So, sometimes if the voltage system is severely stressed, in that case it may act in a reverse direction, means if you are increasing the tapping, voltage will be reduced. So, that will lead to an unstable power system in sense of voltage instability. Similarly, also we saw that if there is a sudden change, no reverse action, sudden change from one tapping to another tapping, you may lead in the unstable zone, and again your system will be unstable. So, the action of transformer are very, very important, especially when you are operating in the lower voltage region. So, these are the various again techniques. Again we are talking about the static voltage stability. We also see the dynamic voltage stability, and then we have to use some bifurcation techniques, and based on that we will see the system performance. So, in the next lecture we will see the continuation power flow methods, because we have to go for the predictor and the corrector method. Those methods are very, very useful, and that we will see how we are proceeding and how we are getting the solution, both upper as well as lower curve of the PV curve, that is a upper side of voltage as well as the lower voltage side. So, with this we will see the next lecture on power this continuation power flow techniques. Thank you.